Now, to take this a step further, we need to be able to say something about cross-sectional geology. So we'll put it in PowerPoint here, overlay that bedrock geology again, and if you were to try to take this structural style and this outcrop distribution and associate it with some representation of cross-sectional structure, you'd have to produce a model that looks something like this, and we'll compare this to a published cross-section momentarily. But what I've tried to produce here is an imbricate lower section, this very tightly buckled middle resistant section that's structurally strong as well as erosionally resistant, and then a much less deformed top of the wedge. And if you were to impose a modern day topographic surface on this, assuming that resistant lithologies were located within that middle tightly buckled resistant layer as well as in that uppermost cream colored layer, you'd end up with some very high topography associated with the very broad, low amplitude but long wavelength structure furthest to the foreland. And then as you move back toward the hinterland, the fact that that little cream colored layer that is very tightly buckled stays at approximately the same structural level over a long distance would put the same rock types in outcrop at the surface over a pretty large area, and that's what's going to produce the repeated Silurian, Devonian outcrop. It's going to give you those really tightly spaced little ridges that are in the middle of the region we're looking at around Franklin, West Virginia. As you move further back towards the hinterland, you produce that very big, broad syncline. The one in the model's not as broad as the one that you see on Google Earth here, but one way or another, that syncline, just like the very large structure towards the foreland, brings higher section rock down to the same structural level as the middle ridge-forming layer, and that's what is allowing pretty high topography to be developed there much closer into the hinterland, where very erodible and weatherable carbonate rocks of a much deeper and farther traveled thrust sheet are now in outcrop to produce the Great Valley of Virginia. And overall elevation distribution here is sort of interesting because the syncline closest to the hinterland there produces elevations that are comparable to what you see in easternmost West Virginia, where Pennsylvanian rock is still part of the present-day topographic surface in that very big, broad syncline. In eastern West Virginia, the highest peaks are about 1,450 meters, or about 4,800 feet above sea level, and in the Mississippian syncline, much further to the east, elevations are around 4,500 feet. So they're around just a little bit, maybe under 1,400 meters. But both of those large synclinal structures have sort of pushed high section but very resistant rock down to the same structural level as much more tightly folded and equally, if not more, resistant rock. But those tight folds compared to the broader synclines are what give you the elevation difference that you see today. So if you wanted to take features in the model, match them up to what you actually see on Google Earth with geology overlay here, the frontal anticline, sort of the very limit of thrust belt deformation, or in this case just folding deformation, would produce that anticline, again where Elkins, West Virginia is located. The syncline within that very broad, long wavelength structure would produce the very high elevations that you see at Spruce Knob or at the Dolly Sods, or even in Snowshoe, West Virginia, where Pennsylvanian rock is still preserved within the modern topographic surface. And moving back towards the hinterland, where thrust faulting has played a more significant role in deformation, you're going to start to see breached anticlines with ridges framing an axial valley. And then you get into this pretty interesting area again, where that ridge-forming sequence, because of the nature of its folding, stays within the range of the modern topographic surface for a great distance, and you're going to look at a lot of Silurian and Devonian rock there in outcrop. That's all you're going to see for many kilometers in either direction. The wavelength of the folding within that domain is pretty low. The amplitude is also pretty low, and the result of that is that you end up with not particularly impressive ridges, but there's a lot of them, and it produces a very rugged landscape overall. Move back into the next good sized syncline, and that's where you're going to bring some higher section resistant rock down to the same structural level. That's going to produce the high elevations that you see at Reddish Knob or Elliott Knob, for example. Those are two very high peaks within that Mississippian cap syncline. And then, in this case, another anticline, and then you're back into the thrust sheet that's bringing in the Cambrian carbonates from much deeper and much further away. So this model is certainly not perfect, but it does a fairly good job of representing what is the interpreted and mapped structural style in this area, and a published cross-section that would run approximately sort of right through the middle of the Google Earth view here would look something like this. This is from Kuhlander and Dean, 1986. It's an older paper. It's a very interesting paper, though, because of the detail with which these structures have been interpreted in this area. It's an AAPG paper. I'll put the link to that or the reference to that in the description. But you can see reasonable similarities between the structural style of the model and the structural style within the strata that are remaining within the Appalachian fold thrust belt wedge. And deep in the model, you've got very brittle layers that are sort of regularly thrust on top of one another. You move up into that brittle middle topography forming layer where you see a lot of very closely spaced thrust faulting, very low wavelength folding, and then above that, towards the foreland, where higher section rock is preserved, you can see those big broad open folds that are producing very broad open synclines that keep high section resistant rock present at the modern topographic surface and produce those really big plateaus that are sort of characteristic of eastern West Virginia. So this model again is not perfect, but by controlling where I put strength within the layer pack, I'm able to produce a structural style that is fairly representative of what's actually been identified in this particular area.